Hello. I'd like to take a moment and share a little visualization of that last typhoon-esque vector field. To do so, I wanted to change the window size that I'm viewing it on, but the program didn't let me, so I ended up modifying the vector field itself so that it fits within the window better. Let me show you here. You can control whether you're visualizing velocities, a force field, field vectors, or streamlines. So let me just look at these components first. So the field vectors are what we're usually thinking of, defined by the vector field. It's just hard to see exactly what's happening, but you can kind of see that they're the brighter colors are the stronger fields in the middle, and they're twirling around a little bit. And then if we look at the streamlines, these are the lines that follow the particles around. And you can see that the streamlines are swirling around and being pulled up along that center axis. And then what's really fun is you can actually slice it. So I'm going to show the Z slice of this vector field. And notice that as I pull it up or down, that horizontal slice stays the same. That's representing how the field's rotation only depends upon the radius and the angle. It does not depend upon Z. So the curl is the same regardless of Z. It depends upon R and theta. Well, actually, in this case, the curl is 0. But the rotation, the external rotation depends only on the two-dimensional point. Now, what about the other slices? This one's kind of awkward because it's slicing all the way through. And if you get to the middle of it, what you see is an increasing profile on the updraft. So you can see that the velocity fields are being pulled upwards stronger and stronger. But as you pull that slice outward towards the edge of the typhoon, it starts to act kind of strange. You're just seeing all the solution curves, how it's being pulled around that typhoon. And if it's closer to the ground, it's being pulled along the ground more before it's being pulled up. And these lines are just projections of the fields upon a plane. So it's kind of hard to tell exactly what's happening. So let's go back. No slicing. See, these are all the streamlines following the particles. And now let's go and look at the particles themselves. Again, you can see that we have that stronger rotation in the center because as we go out farther and further, the magnitude increases. This window size is from -10 to 10 all the way around. So we're zoomed out quite a bit. But we can do a few things like increase the number of points, particles, and these are just created at every spot on the boundary of this cube and the center of the cube, and they kind of move in towards the middle. So they're just populated randomly throughout it. And if we wanted, we could also change the strength of the field to speed it up. But then it gets a little chaotic, so let's slow it down again. There we go. Oh. Very nice. And now I want to compare this with the field with a different divisor. So right now we're dividing by r squared. I want to see how it looked when we divided by the square root of x squared plus y squared, divided by r. So here I've taken out the pull inward and just looked at a rotating field being pulled up by the same updraft. So we can see it looks fairly similar, but we stop that and look at some of the slices. It looks a little different. And what the difference is that we're just going around. We're not getting pulled in like we were before. We take the Z slice. In this case, everything is getting pulled in towards that center. Whereas our case, it's just rotating around. There's no pull in. And that's because the field has only a radial component and then angular component and then a z component. Now, let's look at the streamlines. They're circles, right? They're circles. They should be. They're just traveling around. And over here, our streamlines are converging into it. We describe the difference between these as a spiral sink, or something that is rotating inward, versus a center or orbiting behavior. And now let's try looking at the X or Y slice. Oh, that one's kind of hard to see. So let's look at the X slice. Should be able to get almost to the center. Nope. Since this is based upon numerical methods, you can see that there's a couple of points. It's kind of hard to tell. They kind of bounce around a little bit. So it's a slightly jagged motion on there. These are all the streamlines, or tracking the particles. You can almost see the points of the numerical approximation. Those are all the data points that they're just connecting with straight line edges. So it does look a little bit ragged, but that's the nature of simulation. There's almost on the center. There's our center axis where we have a point of discontinuity you need to watch out for. And last, we can look at the field vectors. You can see those field vectors as we go around are pointing outside of that plane, and as we slide down to the bottom, they flatten out onto the plane because there's no z component. And as we go up, they increase stronger and stronger like that. I hope this visualization and the others we've done in class helps you connect some of the mathematical measurements we've been taking and what the vector fields themselves represent. Now, obviously, most of the applications are to things that are hard to see, like the gravitational field. Like, how do you hold that in your hands? You can't really. You feel it. It's all around us. How about electric field? Again, it's an invisible field of that controls the electrons around us. How about magnetic field? Again, another invisible field, but we can still understand how these things work, how they act on the world around us by modeling the strength of the field, the impact of the field based upon the components of what we have to work with. So for now, signing off. I'll see you in class.